Hello, everybody. My name is Eric McCory.
My name is Eric Bechet.
We are from Worcester Polytechnic Institute. We are undergraduate seniors, and we will be presenting an analog front end for a non-invasive core body temperature sensor. So, core body temperature is just as important of a vital parameter as heart rate, blood pressure, respiration rate, etc. Core body temperature remains relatively the same when compared to extremities, as shown in Figure 1. Core body temperature remains at a steady temperature between 36.5 degrees Celsius to 37.2. If the core body temperature fluctuates too greatly, such as going below 36C or above 37.5C, this will result in hypothermia and hyperthermia relatively. The consequences of either include immensely damaging the body and potentially leading to death. Reasons such as these are why an accurate measurement of core body temperature is so important.
Most methods of acquiring a precise core body temperature involve extremely invasive methods, such as intubation. These aren't really very practical for any applications outside of surgery or an intensive care setting. Other measurement technologies, like the digital fever thermometer pictured and the skin temperature sensor pictured, are just not accurate enough nor fast enough to really give a good representation of core body temperature. However, recently there have been some new methods on finding a non-invasive way to measure, such as the zero heat flux method, the dual heat flux method, and radiothermology. In our system, we chose dual heat flux because it gave a good combination of factors that are important for the design of a good sensor.
So, in order to get a grasp of the different types of sensors, here we present two different types of state-of-the-art core body temperature sensors. The one shown in Figure 4 is a sensor in the market called Core, which is non-invasive and wearable. And this would be an example of what we are trying to achieve. Another example is a rectal thermometer, which is completely invasive but is considered the gold standard of core body temperature measurement, aside from intubation.
So then we come to the new research technologies, and compared to the other methods, dual heat flux does seem to be superior in three facts. One, it does not require the use of an external heating element. This gives us the ability to make a smaller, lighter sensor and a more power efficient sensor, as we don't need to run any heating elements. It performs its functions based on the heat of the subject alone. Second, the dual heat channels that it uses often give more accuracy. Zero heat flux and dual heat flux are very close in design, with the difference being that dual heat flux uses two heat transfer channels of different heights to compute the actual temperature, whereas zero heat flux only uses one. It is also often cheaper and easier to manufacture than many other types of sensors, as it uses simple electronic sensing components and can be made from simple materials such as rubber and plastic.
So, the inner workings of the dual heat flux method include having four temperature sensors, as shown in Figure 5. These temperature sensors can vary from thermistors to analog sensors to digital sensors, etc. And each of them are placed in four different areas. Two would be at the base of the skin, and two would be on underneath a protective cap to protect from ambient temperature variations. These four sensors will have a heat gradient developed amongst them within the insulator, and relating the heat flow, thermal resistance, and temperature difference to voltage, current, and resistance, as shown in Figure 4, can allow us to solve for the core body temperature.
This is the inspiration for our analog front end. A constant current source runs through a set of voltage dividers which are connected to an amplifier and a filter. The resulting signal from this amplifier and filter are sent off chip for digital processing. For the temperature probe, we would expect a voltage output of about 50 to 200 millivolts. Changes from this voltage are then amplified through the systems as changes in core body temperature take place.
So this next figure shows our proposed system diagram, which is powered by a 3-volt coin cell battery. The battery will be able to supply our analog front end as well as a sensor if need be. The analog front end consists of a 3-volt bias circuit for low dropout regulator, another bias circuit, a current source, an amplifier, and a low-pass filter. The low dropout regulator, current source, amplifier, and low-pass filter will be discussed in the following slides.
This is the schematic for our low dropout regulator. The low dropout regulator, or LDO, is designed to take an input of 3 volts and convert this to a voltage of 1.8 volts to run the rest of the circuitry. This particular design was chosen because it does not require large capacitors on its output in order to function reliably, which helps with the size of the final design. The circuit uses feedback from the voltage divider and capacitor on its output in order to control itself and regulate efficiently. We found that the topology gave great regulation accuracy as well as a low power consumption and quick turn-on time, with a final power consumption of about 29 microwatts.
The next circuit to discuss is the current source. The current source is used in order to produce a voltage from our resistive sensor, so we must introduce a current. This topology allows us to introduce a current that is affected minimally by temperature, process parameters, and power supply variations. Not only do we want to be able to introduce a robust and stable current, but we also want to draw as little current from the power supply as possible, aside from supplying the current itself. This design boasts a very low current consumption within microamps, but will be increased by delivering more current as needed. Moving on to the operational amplifier. This topology consists of bias transistors, a differential amplifier with an active load, common source amplifier, and indirect feedback computation. This op-amp takes biases from currents so that we could better control the amount of current at the tail of the differential amplifier. For our design, the most important factors were low power consumption, high stability, and small layout area. Since the rate of heat change is relatively slow, we don't need to have a high-speed design, which allows us to have a lower current draw than if we needed a higher speed.
This is a schematic for our filter. The filter is based off of a fairly simple Allen key design. We implemented pseudo-resistors, or banks of MOSFETs that act like resistors, using the arrays shown in order to create our very low cutoff frequency of 0.4 hertz. By using pseudo-resistors instead of actual resistors, we were able to greatly decrease the amount of area needed to lay this particular filter out. By using a very low cutoff frequency, we are able to eliminate the presence of 60 hertz noise and allow for the passing of even what is considered sudden changes in body temperature.
This figure shows our final layout before adding pads. The 3 larger circuits are analog buffers for our signals. From lower left to right shows the 3-volt bias circuit, voltage divider, LDO, current source, operational amplifier, and filter. The entire layout takes up an area of 0.027 millimeters squared, which is incredibly small.
This is the overall system after we did a post-layout simulation. The blue signal is a 10 millivolts AC waveform at 60 hertz on top of a 100 millivolts DC voltage to simulate noise coming off of our sensor. This is then amplified. The output of the amplifier is shown in red, and it is then filtered with the output of the filter shown in purple or magenta. As you can see, the noise is completely eliminated from our final output from the filter, and we have a flat DC waveform, which is to be sent off chip and digitized.
Here are our references. And lastly, we would like to give acknowledgments to our professor and advisor, Professor Guler, as well as Ian Costanzo, Devdip Sen, Bill Chang, and Franco Baudino, who have helped us in many ways from idea to development to tape out. Again, thank you very much for listening.